Right, good evening ladies and gentlemen, and thank you for coming to our 2025 Darwin Day celebration. My name's Guy Otten. I'm both a Vice Chair of Greater Manchester Humanists and I'm also a member of Northern Atheists local committee that is co-sponsoring or supporting this celebration. Both of those organisations look for members and people to get involved. We're both social and intellectual, and we have interesting meetings. So it's my great pleasure to introduce Dr. Helen Czerski. So Helen is an associate professor at University College London. She's a physicist and oceanographer. She works on the influence of near-surface bubbles. That's an interesting fact for you, for the uptake of carbon by the ocean. She's probably best known for being co-host of Rare Earth on BBC Radio 4. And of course, she was one of the 2020 Royal Institution Christmas lecturers. There's a whole list of achievements I could go into, but I won't, because let's instead turn to Dr. Helen Czerski. Thank you.
And it's lovely to be here. Can you hear me at the back? Yes. Anyone on the back row wave? Amazing. I'm also a patron of Humanists UK, so I have the badge to be here. So thank you all for coming. This is basically going to be a bit like Challenge Annika, because at 8 p.m. I have to be on my way back to London. I have to be out of the door. So here's what we're going to do. I'm going to talk for 40 to 45-ish minutes, and then we'll have some time for your questions. And then at 8 o'clock, I am going to be out the door, right, really quickly, for which I have to apologise. It's a bit beyond my control, but I think we can get through lots in an hour. So I'm here to talk about the ocean, and we don't talk about the ocean. We don't think about the ocean enough. There's a lot of it has to do with the way we see the ocean, really, because obviously, you know, the planets are spherical-ish, and when you look at a sphere, you can't really see all of it. You can't see the bits. And so we tend to, when we unwrap the globe and put it on a flat piece of paper, so we can put it in books and stuff, we tend to unwrap it in a very specific way, and it's one that hides the ocean. Now, this is another way of unwrapping the globe, and it was first drawn by a guy called Athelstan Spilhaus in 1942, so it goes back a bit. But he said something very profound. He said that in order to see the land, we always cut the ocean. And therefore, in order to see the ocean, we must cut the land. So that's what he did. He cut through the continents. He unwrapped the globe. And once you look at it, it's a bit of a funny shape, but most people recognize either Africa or Antarctica first, and then you can kind of see you've got all of the Pacific Ocean out here and all the rest of it. And the reason for plotting it like this is that once you see the ocean like this, it is clearly one big single ocean, a global liquid engine. And that's what I'm here to talk about. As a physicist, I'm very aware that when people think about the ocean, they often treat it as though it's just the filler, where, you know, the sort of blue filler where the fish live. But actually, it's made of liquid water, and that water is doing things. It's not passive, it's not the same anywhere, it's got internal structure and anatomy, and it is kind of astonishing that we don't really look at it. So some of you might know this. Most audiences I speak to, I reckon wouldn't, but I reckon there's at least one or two in this audience who know this before. It's from the Hunting of the Snark, which was a Lewis Carroll poem, a nonsense poem. And I'll tell you, you don't have to read it. The premise of this poem is that, which is a nonsense poem, is that the snark has to be found. A group of people decide they're going to go off hunting for it, and they start their trip by going across the ocean in a boat. None of them are very good at boats, but anyway. And this is their description of what's going on just before it all gets going. And the bellman who's in charge has turned up with a map that's going to guide them across the sea. And this is what he said. He had brought a large map representing the sea without the least vestige of land. And the crew were much pleased when they found it to be a map they could all understand. What's the good of Mercator's north poles and equators, tropic zones and meridian lines? So the bellman would cry, and the crew would reply, these are merely conventional signs. Other maps are such shapes, with their islands and capes. But we've got our brave captain to thank. So the crew would protest that he's brought us the best a perfect and absolute blank. And the joke, of course, in the poem is that the bellman has brought a blank sheet of paper. That's his map to guide them across the ocean. But actually, this pretty much is how we see the ocean. And at this point in history, when this was written, you know, Lewis Carroll might have had a bit of an excuse for writing that, because this was in 1876. And there's an interesting coincidence here, because 1876 was the year that the first global oceanographic expedition got back to London. It had left in 1872, went all the way around the world, and for the first time it tried to systematically sample, like, what's down there, how deep is the ocean, what lives in it. And 1876 was the year they came back with this vast amount of data that took them 20 years to write up. And that expedition revolutionized our idea of what's inside the ocean. So at this point in time, when this poem was written, the ocean pretty much was a perfect and absolute blank from a scientific point of view. But the weird thing is that 150 years later, we still think about it like that. And today we do not have that excuse. This is a very famous image. It was taken before I was born, but this is on the last Apollo mission, 1972. And the thing that was unusual, there were two very famous images that were taken among all the very famous ones. There are two that really stand out in history. And they are Earthrise, which was a picture taken on Apollo 8, where you can see the surface of the moon. This is before they'd landed on it. They're orbiting around it, and they can see Earth rising on the far side, and you can see Earth hanging in space, and you can see it, the bare, barren moon, and then this beautiful planet in the background. And then this was on Apollo 17, and the reason it was unusual is it was the only time during the Apollo missions when they could see out the window in the right direction, where the planet and the spacecraft and the sun were all perfectly lined up. So you can see the full disk of Earth illuminated. You can see the whole thing. And because NASA was just as good at publicity as it is now, they gave it a name. They called it the blue marble. And we have talked about ourselves for 50 years of being the blue planet. And the weird thing is that is where the thinking stops. We go, oh, it's brilliant, we're a blue planet. And then we talk about fish. And we don't interrogate what that blue is. What is it actually doing? And it's this amazing kind of blindness. The Merchant Marine have a word for it in their context. They call it being sea blind. And as a society, we are extraordinarily sea blind. But, you know, maybe there's a reason for that. It's interesting to speculate on why it is that, how do we manage this, right? And I think that there's a part of this which is, you know, there's that famous ancient tale of three blind men somehow finding an elephant, and that bit is never explained. But, you know, the first blind man reaches out his hand and he touches the leg of the elephant and he says, oh, an elephant is like a tree. And then the next one reaches out and touches the trunk and says, oh, an elephant is like a snake. And the point about it is they're all true, but they're all partial truths. And it's only when you see many different perspectives on this elephant that you actually build up a sense of the whole. And I think the ocean is like that. It is so big and rich and complex, and it's got big things and small things and fast things and slow things, and there's so much going on. It is not just a pool of water. So the way to see it, I think, is to look through lots of different lenses, to look at what the ocean is through lots of different stories, through history and culture and animals. And when you've seen enough of these partial truths, maybe then you have an idea of what the ocean really is. I haven't got time to tell you all of the things. That is what you get to do when you write a book. So I wrote the book, and that's got lots of the stories in it. But what I am going to do in the next little while is talk to you, just tell you some of these stories, give you some of these partial truths, and show how they relate to things that we absolutely take for granted. And maybe you'll start to build up a bit of the picture of what the ocean is. So it is by my nature that I can get a bit ranty. There are a couple of rants towards the end, but we'll start with what the ocean is before we get to what the ocean isn't. And the first thing is it's got structure. The ocean's got anatomy. It's not the same everywhere. And I know that probably sounds weird. So let's have a think about this creature here. This is a bit weird. It's a Greenland shark. It's basically a baggy jumper pretending to be a shark. It lives near Greenland in very, very cold water. They swim extraordinarily slowly. Most of them are blind, actually. This one hasn't got it, but most of them have a parasite that's kind of stuck in their eye, so they can't see very much. The thing that is most notable about them is that they're the longest lived large animal that we know of. So they're thought to live to an age of 450 years at least. They don't reach sexual maturity until they're 150. It's not a lifestyle for the impatient. But they live this extraordinarily long lifestyle because they live slowly. And they live slowly because they live in the cold. And in the cold, you know, biochemistry just moves more slowly. So they swim at perhaps a few centimeters a second. They live in almost complete darkness. This might give you nightmares if you're that way inclined. Sorry about that. But, you know, they basically hunt. They can't chase anything, but they are found with seals and fish in their insides. And it's thought that they just sort of slide up on them in the darkness and ambush them. No one's ever seen one hunting, so we don't know. Anyway, the point is, this is a cold water shark. It's called the Greenland shark because it lives mostly up near Greenland here. So this is a map of the North Atlantic, and the colours represent the temperature of the water surface. So the dark blues are the cold temperatures, close to -2, and then these deep reds are the warmer temperatures, which can be around plus 30 degrees. So there's a huge range in ocean surface temperature. So up near Greenland, that's where a Greenland shark lives. But back in around 2012 or so, there was a survey ship in the Gulf of Mexico, which is still called the Gulf of Mexico. And what they were doing was a survey following on from the Deepwater Horizon oil spill. So they wanted to survey the biota afterwards in order to compare, you know, it with what was there before. And so they were putting over nets and sampling things in various ways. They're out in the middle of the Gulf of Mexico. They lowered a set of hooks down the side. It's very deep, so these hooks went about 3 kilometers down. And then when they came up, the thing that came up with them was a juvenile Greenland shark, which is weird, right? There is not supposed to be a Greenland shark here. They're supposed to live up there in the cold water. But the scientists were not that surprised. They were surprised enough about it to mention it in a paper, and there were a few news articles about it, but they didn't think it was that weird. And the reason they didn't think it was that weird is because of the structure of the ocean. So the ocean is organized by density. And there's lots of different things about its structure. This is just the most basic, but it's got internal layers. And one of the strongest layers is that there's this surface, what we call the surface mixed layer, because oceanographers are really good at names. And it can be between 50 and 100 meters deep, kind of depends where you are and what's going on. But this is buoyant, warm water that's floating on top of what's underneath. And then in the case of the Gulf of Mexico, what's underneath goes down 3 kilometers. And there are other layers, more subtle layers on the inside. But the point is, the whole ocean is layered. When I showed you that map before of ocean surface temperature, that is just the surface. If you go down a little way, if you go down a couple of kilometers, it all gets a lot closer to sort of 4-ish degrees C, between 4 and 8 degrees Celsius. So it's cold down here. So that Greenland shark that was, you know, poking around down here, it was in warmer water that's slightly warmer than it was used to, so 4 degrees instead of -1 or 2. But it wasn't way out of its comfort zone. It probably wasn't having a great time. But the point is, it wasn't dead of overheating. It can live in these cold waters. And then telling you about this just to make this point about the structure of the ocean, that just because it looks the same to us doesn't mean the water is the same. And then once you've got this internal anatomy, which gets much more complicated than that, but that's the kind of the starting point, it moves, right? This is an engine powered by sunlight. And so the oceans are shunting around the planet based on the energy they have, how the wind blows, density things, all kinds of stuff. So I want to pick on one area of the ocean just to tell you about a little bit, to tell you about some of the things that have come out of it, and then we'll get to why they're there at the end. So it's a place in the ocean where these things live. These are Peruvian boobies, should any of you be bird watchers, and they are sitting here on a rock covered in their own poo, because basically that's what they do. So the part of the ocean we're looking at here is down the coast of South America. There is a current that runs up the side of South America. It's called the Humboldt Current in Western Europe because of this guy here, Alexander von Humboldt, who was a really interesting so-and-so. He was living around the sort of 1800-ish, bit before but after, and his mother was terribly hopeful that he would turn out to be a very respectable Prussian civil servant. That was what he was supposed to do. And he did not care about that at all. So he went off to study natural history, and he basically swanned around the world, went on these expeditions and observed the world. And the thing that is notable about him is that he was one of the first people in the Western scientific literature to look at connections. This is a period when everybody was very busy, you know, putting things in boxes, following Linnaeus, right? Was it one of those, or is it one of those? Is it a frog, or is it is it amphibian, or is it mammal? How do we break down the boxes to put everything in a box? Alexander von Humboldt looked at the connections, and he was one of the first people to identify human caused climate change, actually to do with forests in Russia and the weather. Anyway, there's a really good book about him by Andrea Wolff that won the Royal Society Book Prize a while ago. So anyway, he was an interesting so-and-so. So he, around this time, came on a ship around the bottom of South America here, came up into the Humboldt Current and went up and kind of observed things along the way. So we're going to be looking at just this thin strip of ocean along the side of South America. It's not very big, but interesting things happen in it. The first thing is these birds. So when von Humboldt came around the coast and he went up sort of closer to the equator and he found these islands that the birds are sitting on, they were covered in not just a little bit of bird poo, but a 30 or 40 meter depth of white, acrid, really stinky poo, right? And the Westerners all thought this is very weird. The locals knew what it was, and they were very careful with that resource. They would take it in small quantities and use it on their fields, and they called it guano, which is the Quechua word for bird poo, and that's where we get guano from. And von Humboldt took a sample of this, sent it back to a lab in France, I think, and they analysed it and found that it was full of phosphate and nitrate. And this was around the time where there was an enormous revolution in farming going on. People were looking for ways to improve the soil. They wanted, they knew that if you ground up bones and put them on the soil, things grew better, which led to a more than a bit grim plundering of battlefields for the bones. So the battlefields of Waterloo were plundered for their bones in order to get phosphates and nitrates to fertilise fields. Fortunately, and you wouldn't have thought this was possible given human history, they ran out of battlefields. And so, and then the guano came along. So an enormous trade started in the 1840s and 1850s where slave labour was used to extract the guano. It was shipped all the way around South America and back, a lot of it to England. But half of this enormous trade grew, about half of it came to England. And what did the English do with it? They fertilised turnips. Now, I don't know how many of you are fans of Blackadder, but this is Baldrick's prize turnip. Worth watching that episode if you haven't seen it. But anyway, Baldrick is very excited about the prize turnip. This is set just before the fertiliser boom began, the guano fertiliser boom began. And just think how much bigger Baldrick's prize turnip would have been if it had been fertilised with South American bird poo. Anyway. But of course, it wasn't just the fertiliser that was interesting about this nitrogen-rich guano. It was the fact that you could use it to make explosives. And there were a lot of wars being fought. The governments were interested in having gunpowder supplies. They needed nitrates. And so there's this extraordinary piece of law, which as far as I could tell is still in the American Constitution. And given the state of affairs at the moment, you've got to hope some people don't find out about it. The Guano Islands Act, where the federal law that enables citizens of the United States to take possession in the name of the United States of unclaimed islands containing guano deposits. So basically all the things the American government's got to think about. They are writing laws saying, if you find any bird poo, we want it. And so people did, the guano wars followed on. This was an enormously valuable resource, and it came from the islands in this very narrow strip of ocean. So we're going to leave the bird poop for a second, we'll come back to it. And then just have another look at the current here. Now this is another surface temperature map, so the same thing with the colours. The reds are hot and the dark blues are cold. And you can see that the Humboldt Current is cold water. There's a cold tongue up the side of South America here. And the thing that region of the world was most famous for at the time was the fish that came out of it. It was extraordinarily productive. So this is the Peruvian anchoveta. It's a small, very oily fish. There's so much of it came out of this strip of the ocean. There was just so much anchoveta. Now, you might be wondering why you've never heard of this fish or why we don't have anchoveta and chips. And there are people who have tried to persuade other people to cook and eat this stuff. They made recipe books and tried to do a marketing job and convince them that it's very nice to eat. But basically, it's really oily, it's really strong flavoured, and it's thoroughly disgusting. So the recipes never worked. But that didn't mean humans didn't fish it out of the ocean. So a lot of the anchoveta were taken out of the Humboldt Current. And there's this weird thing that over a sort of 25-ish year period after 1950, the amount of fish caught went up enormously, it tripled. But the amount of that fish that was eaten by humans stayed the same. So there was all this other stuff, all this other fish that was going somewhere that wasn't into feeding humans. And the place it went is, well, you know, so a fish is a beautiful evolutionary example of how to live in the ocean, and it's elegant and, you know, all the rest of it. But fundamentally, if you kill it, dry it out, grind it up, and put it in a bag, you get this stuff here, which is fish meal. And the thing about fish meal is it's really protein rich. And this became important a bit later on. So we've come forward now to 1960. So after the Second World War and the pig clubs and all of that in the UK, people decided they quite like keeping pigs. And pigs are fine, but they need a lot of protein. And if you can't supply enough protein, you're not going to have pigs. So fish meal was the food of choice. So in the 1960s, people were taking enormous amounts of fish out of the Humboldt Current, shipping it to Britain and feeding it to the pigs. And that's where the bacon rashers came from. And of course, you know, humans not being in the nature of understanding the word moderation, this just went up and up and up. In 1964, Peru, in that narrow strip of water, caught 40% of the entire global fish catch. It's an astonishing figure. 40% of all the fish in the world came from this really narrow strip of ocean. And of course, you know where this is going because it's where it always goes. You take and take and take until one day there just were no fish. And that day came in 1972, and the price of British bacon doubled overnight because they basically ran out of fish to feed the pigs with. So the point is that we've got two enormous globe-spanning trades here out of things that came out of this very narrow strip of current. So what is it that's going on, right? Why is it there? And it starts with the layers that I showed you before. But the thing about this ocean is this should be dead. And the reason an ocean that looks like this should be dead is that in order to grow things in the ocean, you need two things. You need energy, which comes from the sunlight, which is up the top, and you need nutrients, which tend to be, for various reasons, down below. So there's this paradox. The ocean should be dead because the energy is at the top and the nutrients, the raw material, is down below. But it just so happens that in the Humboldt Current, the wind and the spin of the earth and various other things conspire to push that warm surface layer away from the coastline, and then you get cold water welling up from underneath. And then you have sunlight at the top, you've got nutrients, you generate lots and lots of life because you've got the raw materials and the energy. That phytoplankton feeds the fish, so that's why there's vast quantities of fish. That's where all they came from. And because the paradox is broken so successfully, the ocean suddenly becomes extraordinarily productive, which means it grows lots of things. And then the poo is not just that there's fish for the seabirds to eat, because once they eat fish, they go back to their island, they sit there, they poo. And you might wonder, well, why it is that bird poo is so much more useful than bird poo in Europe, right? We've got plenty of birds, they produce a similar amount of poo per bird. And the answer is it's because the Humboldt Current is cold, and because it's cold, it stops it raining. And so because it doesn't rain, the guano doesn't get sort of washed away and chemically altered. So it stays in this pristine state, which makes it extraordinarily valuable. So basically, humans just came along and went, oh, look, fish, guano, amazing, we'll have those. But it's not a sort of, it's not like the lottery, that they just appeared. It's because the ocean is doing something underneath which produces the conditions which make that happen in that place. And this happens all the time. We get news stories here that say, oh, there are loads of jellyfish off Cornwall today. Like jellyfish just appeared. Today it's jellyfish, tomorrow it might be clarinets. And that's, of course, that's not what's happening. What's happening is there is a really intricate and interesting system just underneath the surface. And the way it turns produces patterns, and we only see the consequences of that pattern at the surface. So we don't really see into the ocean, but it's doing things all the time that directly affect us. So once you've got this moving engine, what's it doing? What's it carrying? Because if you're moving water around, water is a very good vehicle, and the ocean does carry passengers. So I'm just going to give you an example of one slightly bizarre passenger. I promise I'm not making this up. So we've come across the world now to the coastline of the African continent here, and there's a little town there called Kimbiji on the coast. And you can see that it's on the edge of the Indian Ocean, which is the sort of place where you get sea turtles. And so the beaches of Kimbiji are steep. They're exactly the sort of beaches that female sea turtles like to haul themselves up. This is my sea turtle impression. Haul themselves up the beach in order to lay their eggs. And of course, because sea turtles are often endangered, people are, want to watch them and make sure they're not being disturbed by lights and people and all that kind of thing. So there are quite often sea turtle watchers on the coast in Kimbiji here. And one morning, 15 or so years ago, there were 2 sea turtle watchers, locals, and they were watching in the sunrise, and this sort of big thing began to move out of the ocean, kind of big round thing. But after a while, they realized it wasn't pulling itself like a turtle. It was walking, and it was walking because it was a tortoise. And this is it. This is the Kimbiji tortoise. Now, in case any of you were now questioning everything you thought you knew about the tortoise, it's not supposed to do this, right? It had been at sea for a long time. It's covered in barnacles. They thought it had been at sea for at least 2 months. And eventually they worked out that it probably drifted from this island called Aldabra over there, 800 kilometers. Now, this is not supposed to happen to a tortoise. But it does happen that tortoises apparently like paddling in the shallows, and that means they sometimes get washed in, and that means they sometimes get washed out to sea. And if that happens to them, they're probably a goner, but they have a few things in their favor. Thing number one is they've got a big long neck that can act like a snorkel, so they can keep their head above the waves and they can keep breathing. Thing number two is that they can go without food or fresh water for a long time, so that's very convenient. The real kicker is that female tortoises can store sperm. And that means if a lady tortoise, takes care of business before she floats out to sea, if she is lucky enough to arrive somewhere else, she can start a new colony all by herself. And it had been suspected that tortoises might occasionally float like this, but no one had actually seen it happening. And the reason that it had been suspected that tortoises do this is because there's a couple of places where tortoises are not supposed to be. And, oh, that's a tortoise that fell in. So let's just go back across to the other side of the world. That still catches me out. There's some slides I haven't corrected. And anyway, I do know how to spell Galapagos. So the Galapagos Islands are famous for their giant tortoises, right? But the Galapagos Islands are volcanic. They have never at any point been joined up with the South American continent. And you can see where this is going. How does a Galapagos island get a tortoise? Well, the answer, those are the famous Galapagos Island tortoises, the answer is the Humboldt Current, right? It comes all the way up the side of South America, and then just before the equator, it turns off and it crosses the Galapagos Islands. And so over a very, very long period of time, and this is true, it seems that enough tortoises kind of were clumsy on the coast of South America, got carried along and then got carried across the path of the Galapagos Islands, washed themselves up, started new colonies, and eventually underwent island gigantism and all that thing and formed a new species. And that is how the Galapagos got its tortoises. And I promise I'm not making this up. It is extraordinarily unlikely, but it has happened enough times that the Galapagos has tortoises. And actually, in the other example, the other place where this has happened is the Aldabra tortoise, because although that one went from the island to the land, those are reversing currents. And so the reason the Seychelles also have giant tortoises is that giant tortoises are apparently getting carried both ways. I have no idea whether anyone has tested whether these particular subspecies of tortoises are particularly clumsy, but definitely at some point in their evolutionary history, their ancestors all did one very silly thing in common. So the point is that if an ocean can carry a passenger as big as a tortoise, it must be able to carry lots of smaller things. And it's the smaller things that are really interesting. And a lot of them are so small we can't see them. So this is concrete. I don't know how much you think about concrete. It tends to be seen as a scourge of the modern world, unless you're an architect that's really into brutalist architecture. But the Colosseum, a lot of its foundations are made of concrete. The Romans were really good at concrete. And this is the very famous roof of the Pantheon, which still, 2,000 years later, is the largest unreinforced concrete dome in the world. And it has lasted 2,000 years. The walls are phenomenally thick in order to hold it up, but it worked. So the Romans are really good at concrete. We tend to see concrete a bit more like this. It's the reason we have skyscrapers. There's a debate about how high you could build a skyscraper without concrete, but it's certainly not that high. And when you think about it, though, from the point of view of an architect, concrete's amazing, right? It's like an artificial stone that you can make any shape you want. It's incredibly convenient. So there's a lot of concrete in our lives, and that's why. And the thing that is interesting here is, what is it you need to make concrete? Because there's a building block at the base of it all. So if you want concrete, what concrete is a combination of cement and aggregate, which is kind of gravel and sand. So the cement is the key ingredient. So what do you want? How do you get cement? Well, cement, to make cement, you need lime, calcium oxide. The place you get calcium oxide from is calcium carbonate, and calcium carbonate we get from limestone quarries. So that's where our concrete comes from. So now let's kind of flip that on its head a bit and look at something else. So this is southern England, and this is a true colour satellite image. And these light blue areas here are phytoplankton blooms. So phytoplankton are the tiny little drifting passengers of the ocean. And if you get the right conditions, if you get the nutrients and the temperature and all those kind of things in there, and they all line up, you can get these huge agglomerations, these enormous explosions of life. And in this case, it's almost all this little thing here, which is a single cell. It's called a coccolithophore. There's lots of species of it. And they've got these beautiful little calcium carbonate platelets on the outside. Now, the thing about this is that calcium is a really important building material. Calcium itself, just the element, has enormous potential as a building material. And the place that these little things get it from is that they have to collect it from the water around them, one ion at a time, in order to build up their beautiful little shells. And the thing that happens when you have loads of them all at once and they all grow all at once is that the predators can't keep up. They're bigger, they take longer to grow. And so when you get a big bloom, quite soon afterwards, you get a big death, basically, and the uneaten coccolithophores will just drift down to the seafloor, and over very, very long periods of time, they will just build up and build up and build up in layers. And over geological time, if they are compressed, and if geology is on your side, and they get turned into rock and brought back up somewhere else, eventually you get the White Cliffs of Dover. And the White Cliffs of Dover is almost entirely made up of very tiny calcium-based single-celled organisms like this that collected their calcium atom by atom. And the thing I like about the White Cliffs of Dover is that, you know, we associate chalk traditionally with school, and I really like the idea of English and maths and history and geography being taught by scraping on a piece of slate with tiny bits of sea creature. Like, for centuries, I really like that idea, but it gets one better than that. So you're not allowed to take bits of the White Cliffs of Dover today. Very sensibly, they stopped people because otherwise there wouldn't be any left. But you can get hold of a bit if you go to somewhere who took it before it wasn't allowed, which is always a good idea. And so if you go to the Royal Institution of Great Britain, ask very nicely, you can borrow a piece of the White Cliffs of Dover. And if you're me, about 10 years ago, you borrow it from them, and then you can draw a coccolithophore with itself, which made me very, very happy. I am a terrible artist, but I like the circularity of this. So anyway, the point is that there are no other, so you can see here that these tiny little creatures collecting calcium atom by atom, this is what has collected the calcium in order to make limestone, which allows concrete to exist. So it turns out in Earth's geology that calcium is almost always very, very dilute. So in the metamorphic rocks, the rocks that come from either deep in the earth or that come out of volcanoes, concentrations of calcium are really low. There is no source where you can just extract calcium-based minerals. But it turns out that as the calcium was eroded by acid rain, it ran into the oceans. The oceans have lots of calcium carbonate. That provides the raw material for the tiny little sea creatures. Then you get your limestone, and that's where concrete comes from. And what that means is that the concrete foundation of this building, the concrete that you have been walking around all your lives, the concrete that holds up the Canary Wharf skyscrapers, the concrete that holds up the Burj Khalifa in Dubai, the tallest building in the world, where I was a couple of weeks ago, all of that is only possible. Every single calcium atom is in it because it came through tiny little sea creatures over geological history. So if you want an example of how the ocean matters to the modern world, you couldn't get more convincing than that. We're literally built on something the ocean built for us. And I wrote a column about this. I had a column in the Wall Street Journal for many years in the Sensible section and in the Weekend Review. And artists, the illustrators of my columns over the years in various columns, there are 2 separate occasions when they've drawn 8-sided snowflakes, which is just, what's the one thing everyone knows about snowflake, right? Anyway, but this time the artist made up for it, and this was his illustration for the column, which I just thought was beautiful. Anyway, so the passengers of the ocean also influence us here on land. Right, we're going to get some rants on what the ocean isn't. And the first thing on the list is the ocean is not silent. Why would anyone think it was silent? Because this guy here, Red Beanie Man, Jacques Cousteau, who was in there, he helped invent the aqualung, which became the scuba apparatus that we're familiar with today. And then he helped the development of underwater cameras, which he then used to film the underwater world. And one of the things he created was this very famous film that he called The Silent World. And it won the Palme d'Or at the Cannes Film Festival in 1956. It was phenomenally famous. This was humanity's introduction to the ocean. So you would think that I would be a big fan of Jacques Cousteau in this period, but I'm not, for 2 reasons. One of them is that the film has not aged well. I don't know how many of you have seen this, but if you watch it with modern eyes, doesn't look so good. They ride sea turtles, they blow up reefs, they run over a baby whale and film it. Everything that they find in the ocean somehow ends up with the very enthusiastic chef on board the ship. Like literally everything that you're not supposed to do in the ocean is in this film, and he's proudly showing off. Like he would be in prison if he made this film today, and that is absolutely not an exaggeration. He would be in prison several times over, which is encouraging in a way because it means that we have changed in our societal norms. Anyway, so I mean, to give him due credit, in his later, as time went on, he did become a bit more conservation-minded, but he definitely wasn't at the start. So that's one problem I've got with this film. The other one is that the ocean isn't silent. Like, it really isn't. He was a free diver before he was a scuba diver, so he could dive down into the ocean and not have the noisy bubbles that come from scuba. He must have known the ocean was full of sound, but for dramatic reasons, he called it the silent world anyway. And so the ocean's great introduction onto the world stage came with this completely nonsense title, which is just offensive. Anyway, so just the interesting thing about sound in the ocean. So the second half of my book is written in terms of messengers, passengers, and voyagers through the ocean. And the thing about the messengers, that's sound and light, is that there's an interesting contrast between the way they are in the ocean and the way they are on land. So up here on land, we take for granted that light is a long distance messenger, right? We can see the moon, even though it's a very long way away. We can see distant mountain ranges. We can see people on the, a long way down a shopping mall. And sound only travels a very short distance by comparison, right? We know that if we step out onto the street here, we won't be able to hear the conversations on the other side of the road. We just take it for granted. So sound is a short distance messenger on land. But in the ocean, it's the other way around. Even though we think of water as transparent, it's actually not very transparent. Light will go through it for a couple of 100 meters at most in really clear conditions. But underwater, it's sound that is the long-distance messenger. If you want to understand the big picture environment in the ocean, you have to understand the sound. And so I just wanted to show you one thing which just illustrates the importance of sound in the ocean. And it's this thing here. So The best place in any museum is the behind the scenes bit, right? The stores of the museum. And this picture was taken, I went down to the basement of the Natural History Museum in London, and the hands you can see here are the hands of Richard Sabin, who is their curator of mammals. And he was kind enough to show me these. They've got lots of samples like this. They're like kind of little sticks. They're about this long. And you can just see it on the picture here. They've kind of got these stripes going up the stick. Now, it's the sort of thing you might expect to see in the museum. You would never guess what it is. It's whale earwax. And this raises a lot of questions, starting with why have whales got earwax? So the short version of why whales have earwax is that whales evolved from land mammals that were about the size of a medium-sized dog. So 50 to 60 million years ago, there were these four-legged things running around on the land, and they are the ancestors of whales and dolphins. And they gradually took on a more and more aquatic lifestyle. And as they did, obviously they changed. Evolution picked out the most successful strategies and they changed. And so the first thing is that if you want to swim underwater, being streamlined is a really good idea. So sticky out ears, that's not very helpful. So the outer ear, which is the sticky out bit, that got smaller and smaller and smaller. But that's only one part of our ear. Inside there is a middle ear and an inner ear. And they were fine. And so the outer ear got smaller and smaller until it disappeared and was eventually covered over by a flap of skin. But the whales didn't really care, the early proto whales, because at that point they were hearing the same way that we hear in a swimming pool. They were hearing through the bones of their jaw and their skull. So if you put your head underwater in a swimming pool or in the ocean or something, it sounds different. And it sounds different for two reasons. One of them is that the sound actually is different. And the other one is that you are hearing through the bones of your skull. The sound can travel up your jaw and get to your inner ear, kind of round the back, if you like, and you can still hear. So all of this apparatus, your middle ear, which is what it's there for, is to take sound in air and convert it into sound in water, because the sensing bit in the inner ear is in water. That's no use to you when your head's underwater. So whales evolved to hear through the jaws of their skull. The sound just comes in, hits the jaw, goes straight up, job done. But evolution is not very tidy. So even though the hole kind of got closed over with a flap of skin, the inside kind of stayed the same, and that meant it kept producing earwax. And so over the life of a whale or a dolphin, the wax just is kind of pushed up the tube, and then it just gets stuck against the end, and then more layers come up behind, and that's where you get these plugs from. They're just wax that has been pushed up against the outside of the whale. And it's got nowhere to go, so it just stays there. And if you look at this is the life-size model of a blue whale in the Natural History Museum, and if you look just behind its eye there, so where the sort of flaps of skin are, so we're up behind the eye on that bit. Just behind the flaps, you can see even on the model there's this tiny dimple, and that is where the ear of the whale that's where the hole used to be, but it isn't anymore, and now there's just this dimple of skin. But behind it, there is this tube that is full of earwax. And curators, scientists early on, found these things and thought, well, that's got layers in it. They look like tree rings. That looks useful. We'll keep hold of that. And so the Natural History Museum of London and the American Museum of Natural History have an enormous number of these whale earwax plugs. But this is the brilliant thing about museums, right? They just collect things because it seems like a good thing to do. And then a few years ago, they could look back, and between the two of them, they could say, actually, not only do we have lots of these things, but we know the year the whales died because we know how the sample got to us. And that means that if each little plug of earwax is a whole record of the life of the whale, and you can line up the plugs of earwax going back in time, you can basically reconstruct the average state of life for whales going back 150 years. And so that's what they did. And if you've got that record, what do you look at? What do you choose to look at in that record? And they chose a stress hormone, cortisol. So this is the only graph. Sorry about the graph, but anyway. So there we go, 1870, we've got time along the bottom, coming forward 150 years, and the black line is the one to pay attention to. So this is how much cortisol there is, and the more cortisol there is, the more stressed a whale is. And this is an average over global whales, global baleen whales, so fin, sei, and blue whales. And you can see that there's quite big changes, like sometimes the whales are really, really stressed and sometimes they're not so stressed. So what stresses out a whale? Someone trying to kill it. And so on the other y-axis here, in blue, we've got the number of whales that were being killed for commercial purposes, because whalers were really good at keeping records, right? There was money in it. And you can see that they correlate pretty well. When there's more whales being killed, their whales are more stressed. That sounds pretty sensible. And this huge peak here in the mid-60s before commercial whaling was banned. So that's all fine, except there's one place where the pattern doesn't match. And it's this bit here in the Second World War, where you can see the humans were busy killing each other. So they weren't killing whales. So whale kills go right down. But whale stress goes right up. And the explanation for this is the sound. Guns, bombs, destroyers, torpedoes. The sounds of battle at sea are stressing out the whales because that sound is filling the ocean. And these are creatures that organize their lives through sound. And so it's literally written in their earwax. It's quite an astonishing thing. The importance of sound in the ocean as a messenger. I didn't show this before just for simplicity, but whales are getting stressed again. I'm sure you can guess why, but the pattern has again been broken, but at this time it's very definitely the fault of humans, but in a different way. Okay, this is the proper rant. I will get through this rant really quickly and then I will miss the last bit and then I will still finish on time. Because I really care about this bit. There is this thing you may have heard said occasionally, you may even have said it yourselves. We know more about the surface of the moon, or possibly Mars, than we know about the deep ocean. And if Helen ruled the world, no one would ever say this ever again. It's wrong, it's bad, and it's rubbish. And if you take one thing away from this talk, you will never say that ever again, and you will challenge anybody you hear who does. Because it's bad and awful and horrid. And there is science behind this. It's just rubbish. I mean, it's rubbish and lazy, right? It comes from a grain of truth. It comes from a time in the 70s where the shape of the moon was mapped with a higher resolution than all areas of the ocean. So that was the grain of truth that became twisted into this other thing. But the problem with that is it sort of assumes that the map is all that matters, right? The shape, if you know the shape of a coastline, then we know everything we know. And that is kind of how the history of Western exploration proceeded, right? People were sent off in ships, usually by a king or somebody. They went to some remote area, they spent some time with their sextants and whatever, they drew a map, they named bits of it after their mates, they stuck a flag in the middle and they buggered off home to get lots of gold, right? That's kind of how the story went. And the thing is that you don't know anything about this, right? Maps are not the point of exploration. We need an updated, more modern version of exploration, which is to do with understanding mechanisms, not just drawing maps and going home with your name, having named something after your mates. That's thing number one. The other thing is there is so much more happening in the ocean. The moon is very nice, but it has not changed for 2 billion years. And the ocean is doing all these things. It's got a third dimension for a start. It's got water which is moving about and doing things. It's got things living in the ocean. So this is just a little thing that is bioluminescing in the deep ocean. It's full of interesting geology, and it's got this. Now, promise that this thing I'm about to tell you is true. There is a type of worm in the ocean. There are 3 species that do the thing I'm about to describe to you. There's a type of polychaete worm that lives, the way its life cycle goes like this. It's a little sort of baby juvenile thing, and then it finds itself a sponge. And a sponge is, I mean, that's what sponges originally were, right? It's this kind of open network thing, which has got just enough animal in it to count as an animal, but it's mostly a solid structure with lots of holes. So this juvenile worm finds itself a sponge, and it sticks its head down the bottom of the sponge. And then as it grows, its tail grows upwards into the holes in the sponge, but it doesn't just grow into the holes, it branches and branches and branches and branches. And as it grows out through the sponge, it keeps branching until by the time it gets to the surface, the part of the worm that emerges to be seen by the rest of the world is 1,000 little anuses crawling around on the surface, looking like they're poking about, looking for things. And it gets even better because clearly when it comes to the dating game, this worm is not doing very well, right? You're not getting out of your sponge to go and see someone else because you're completely woven into this thing. So what happens when it comes to be time to do that is that the little anuses grow eyes, and they get rid of the digestive bits, and they grow gonads, and then they break away and they swim off to the surface all at the same time, all male or all female at once, and they get on with the mating up there with some other things that have come from elsewhere. They all coordinate it. And then the juveniles sort of float back down to the bottom, find themselves a new sponge and carry on. You do not get that on the moon, right? There is more interesting science in that one worm than there is on the whole of the moon. And the moon is very nice. I am not anti-moon. But the problem with saying that we know more about the moon than we know about the deep sea is that it makes the deep sea sound like the moon. It makes it sound as though it's a barren, dead place with nothing happening, and that is not true. So never say it again. Rant over. There's some fish. Tuna, very cool. We're at the voyages, very quickly on the voyages. If you're a massive ocean predator, you've got all this structure, you've got all these interesting bits of ocean, where are you going to go to hunt? If you're a big enough and strong enough fish, this is a bluefin tuna, they are extraordinarily powerful, agile, they can go anywhere they want. Where do you choose to go? And this is just one example of that. So we're going to zoom in on this bit of the ocean here, North Atlantic, and there's currents that it gets drawn, the Gulf Stream coming across up the border, up the American coastline and turning across the Atlantic. And it's always drawn like this, and it's not like this. Because this is a current of hot water, a river of hot water that's traveling through other water. So of course, interesting things are going to happen. It's not got fixed boundaries. So basically to the north of the Gulf Stream, you've got cold water. To the south, you've got warm water, and you've got a hot Gulf Stream coming through the middle. And as it travels, it starts to meander. So it wobbles, and then the wobbles get bigger and the wobbles get bigger until eventually you can get wobbles that just break away and form little spinning areas all by themselves. And what you get when that happens is that in the cold water to the north, you get little spinning islands of warm water that float off into the cold water, and to the south, you get little spinning islands of cold water that are doing the opposite thing. These are real. They're about 50 to 100 kilometers across. They're called mesoscale eddies. They can last for several months, up to nearly 2 years in some cases. And they carry little ecosystems with them. They just sort of, float off into those areas of ocean. And we know from fishing records that what tends to happen is that the bluefin tuna tend to be found in the warm ones spinning that way. The yellowfin and the big eye tend to be found in the cold ones spinning the other way, and the swordfish hang about on the edges. And the point about this is that these creatures they operate in a mostly predictable ocean. They don't know exactly when one of these things is going to spin off, but they do know that if they go to the Gulf Stream at a certain type of year and hunt around, they will find a little spinning island, and then they just stay in it feeding, because that's the rich feeding ground, until it's time to go back to their home waters. So the point is they are looking for predictable features inside the water, and that is how voyagers operate in the ocean. They are moving through its structures. Okay, oh yeah, here's a little video of it happening. So this is a computer simulation, but based on real data. So you can see these little spinning islands. All right, so we're getting to the end now. How to think about the ocean. So I think each of us has 3 life support systems. We've got our own body, we've got planet Earth, and we've got the infrastructure of our civilization. Each one of those is a life support system for us. And the ocean is the beating heart of our planetary life support system. It's not just about a color. The way it operates completely defines our world. And so in a few years, maybe this year, maybe next year, the Artemis missions are going to take people, not just men this time, people back to the moon for the first time in 50 years. And the thing about that is no one since the Apollo missions has been far enough away from the Earth to really see our planet, to really see what we are. So at some point in the next couple of years, human eyes are once again going to see the blue marble from space. And this time we have to understand that the blue of our blue planet is not just about a color or a filler or a pretty thing. It's about our identity as citizens of an ocean planet. And the light that travels out from Earth is kind of like our signature on the universe, right? Anything far away, if it looks, this is what it sees of us. And this planet has been broadcasting a message for far longer than humans have been around. And this time, when we are far enough to see it, we have to look at that message and really understand what it is, because it's a very simple message. It says, we are ocean. Thank you.